Good evening, everybody. So we start now. Today we again are going to have the lecture devoted to some basics of category theory and its language and some specific notations. As we have agreed, it is assumed that the listeners are in good terms with category theory, so I just mostly skip the basic constructions, though some of them are not quite standard and some notations are not quite standard, and we train ourselves a bit using the notations from the first lecture. To begin with, we start with an arbitrary category C, and there is no other way than to fix in words that it is a category. So we are going to use the calligraphic C and around, usually just for an arbitrary category without any additional assumption. And so I remind a bit non-standard, the first of non-standard notation. This means that A is an object, an arbitrary object of the category of C. So we introduce the category. I don't think I should duplicate the word or just write over A, which we are going to denote like this. This is an element, this is an object of, so to say, non-linear. Oh no, we don't use duplication here in the definitions. So I give a linear definition, but of course it is recommended following the word over to think about it in a bit non-linear way. I'm going to be clearer in a while. So it consists of pairs X and Xi, where X is an object of C and Xi is a morphism from X to A. So as usually we do not define the morphisms explicitly because they are natural in every sense in the world, and here whenever we have, and here is a non-linear element of this language. We better think about an object of this category over A like this, and having Y together with eta. We define a morphism from one object to another to be such a morphism in the category C. As usual, we have agreed that just drawing an arrow between the objects of some category, we always mean that it is a morphism of the category. And in the same way, without wasting time and chalk for standard conventions, whenever we see a diagram, we assume that it is commutative. So I'd like to give a seemingly trivial but a very important example. I would call it the Grothendieck relativity, not the Einstein's one, but another one as important as well. In fact, the course is mostly devoted to the Grothendieck's drastic change of algebraic geometry, and maybe it is rather natural to call pre-Grothendieck algebraic geometry the classical one and post-Grothendieck geometry the modern one. So, well, the main idea of our course is reflected in its title, but there is another idea, maybe hidden a bit, but it is true that Grothendieck never considered the isolated objects of algebraic geometry. And as I read, he was the first one to use the vertical arrows. So, and now we see how this concept in a very natural way transform to this special approach to the objects of algebraic geometry. So suppose we have a field K. Here is our notations for that. And what Grothendieck suggested to consider was just the category. We have not introduced the special notations for algebraic varieties. Let's assume it now. Well, and let us understand it as the category of good enough schemes, well, separated of finite type and so on. But deciding to do the algebraic geometry, really geometry, not, well, scheme theory and not the number theory, we consider this category over such a funny object as the spectrum of a fixed field. It is funny because, well, this spectrum is a point, and for a beginner it is sometimes strange to consider the diagram over the point. So theoretically this point doesn't change anything, as well as any final object in any category. However, this point has lots of automorphisms. This point has lots of automorphisms, and it is quite an important decision. And say, said theoretically, the real algebraic varieties, well, considered as the object of such a category when K is reals can coincide theoretically or topologically with the same object over C over complex numbers, but they are different objects of different categories. So this is just an example. A dual one is under. It is not so good in terms of the nonlinear semiotics. We just reverse all the arrows. However, I spend some seconds to write it down. So this it's again the set of pairs where X is an arbitrary object of the category, but Xi, on the contrary, is a morphism from a fixed object to X. Of course, with the same condition and the arrows reversed. Maybe I write it once to confess that nobody, as far as I know, considers the diagrams like this. So the word under is something conventional, and well, it is not a traditional one. I just don't know how to name something dual to be over. However, again, I want to give quite a meaningful example. So suppose here we have A, or better perhaps R. Oh no, let it be A unknown. Though an element of the category ring, of course the non-commutative ring also can be called unknown. That's why the letter A is quite appropriate. And well, the category of rings over A then is exactly the same as the category of A that bears another standard notation and could take place among our names for the standard categories, though depending on a fixed ring, the category of A algebras. Maybe I'd like to ask both the people from this room and the distant listeners, is anything wrong in what I've written up to now?
Maybe commutativity assumptions.
Say it louder, please.
Maybe commutativity assumptions.
Oh, no. Well, no puzzles. I'll try to avoid puzzles. We're going to discuss today the equality in the equality sign in the category language. Usually it is a 4-in-1, and we'll see soon that there is no equality in category theory between the objects of category theory. And more than that, there is no such thing as the equality of categories. So what is written here simply means, again, sorry for the introduction of non-standard concept like this. We are, among other things, we are discussing language, and it is nothing but the synonym. The two objects, the two expressions are totally interchangeable. They just mean the same. Therefore, anywhere in any text you can replace one by another, whatever you like more. Okay, but I prefer the left one just because it is much shorter. In the standard algebraic course, defining the A algebra, you should say that, it is an A module together with multiplications that satisfy those and those axioms. This is much shorter and again shows the effectivity of the category viewpoint on the very standard objects. Now, so if there is no questions about these standard concepts, I erase them.
Sorry, in this simplification we shouldn't.
Sorry, again, just a bit louder, please.
In this simplification of
The synonymic.
Under A, we I think we should melt that A in the center of a ring.
Sorry.
Or A just or we should consider only commutative rings.
Is it so? What I'm sure about that we should consider rings with a unit that I always do. And is there something wrong with non-commutative rings?
I thought that there is axiom that if we multiply.
It seems that there is associativity, yes. Well, thank you very much. In any case, I think you are right.
Maybe it's
well, I'm not sure and not fluent in the non-commutative algebra. The simplest, thank you very much for this remark, and the simplest thing to do is to assume that the ring, we consider only commutative ring, and then your question disappears, perhaps, yes. Okay. Any questions about what is written here? Well, then I erase these, what was introduced up to now. I've met such notations in many sources. The next one is not standard at all. So the full, though the concept was mentioned during the first lecture, and we discuss the full subcategories. Perhaps not in such detail in which this important concept deserves, but just notationally. And maybe I just make no attempts to write down something general, but give a couple of examples underlying one of them. So I'm using the angle brackets with some property, perhaps mark it now, property of objects. And said theoretically, it is similar to the standard defining the subsets, like the set of elements such that something, such that they satisfy a certain property. It is. So let's suggest some obvious examples. So the category of finite set was mentioned during the first lecture, and well, its category properties were underlined and were related to the category of indices of coverings. In many considerations related to topology, we can concentrate on the compact topological spaces and therefore consider only finite coverings. However, it would be a great mistake to think that therefore they are numbered in some standard way. Then there is another obvious category. Oh, sorry, I did not comment on the word full. Well, it is just obvious in the subcategories, at least defined this way. We consider the same morphisms as in the larger categories, and it just is related to the word full. And then there is one that I'd like to distinguish out of that, so and relate the two of today's notation. The category of field itself is strange enough because there seems to be no interaction at all between the fields of different characteristics. So what is really natural to consider the fields over something, well, and we can write, since there exists a smallest field of any characteristics, so there is this K is either Q or F sub 2 or F sub 3 or F sub 5 or and so on. This notation works also for the primary numbers for the powers of primes, but they belong to such categories over the small fields. So it could seem that studying fields, we can study all these categories separately. And well, this study, from the point of view of classification, the concept which I hope we discuss today, seems hopeless unless we impose some conditions. And then the most natural and strong condition is being finally generated, and I box this category as one of our major goals, and some claim that in a very weak sense we are able to classify the objects of this category in a very weak sense. As for the previous two examples, we can classify their objects in much stronger sense. So perhaps that's all for the new notations, all for today, I hope. Well, any questions or comments from anybody? Well, then our next today's topic is small It is a standard concept again, and which is more important, is essentially small. That is not quite standard categories. As for the small ones, we have discussed the one of the examples during the first lecture. I add another standard examples. So it was pronounced that the object of a small category constitute a set, and then the partially ordered set is transformed to the small category with the morphisms that were defined a week ago. And another one is that for J a group, it is a bit better because I'm unable to write down the calligraphic J. So, but let's write something. The J set with a multiplication operation. Well, let me try to write something like that. J with I use words to avoid the equality with only object say star and the group of automorphisms of star being by definition J. Well, the automorphism group was not introduced, but perhaps everybody understands that it is just a group of invertible self-morphism, or in better invertible, better endomorphisms constitute are constituted by the morphisms of object to itself, and automorphisms are the invertible endomorphisms. So these, I think the first example does not seem artificial anymore after we have used it during the first lecture in the definition of a presheaf. As for the group, this one element category, there are also situations where it gives, using this category gives a great economy of language from one point of view, and from the other, the corresponding picture, though being abstract, is sometimes quite fruitful, considering these directed loops, the bunch of directed loops with the composition defined by the group operation is sometimes quite productive. So this is what I'd like to say about small categories, and that's all. And now another concept that could seem useless, like discrete categories. So let's study another kind of duplication with quantifiers. So suppose that for any two objects, the category is C is discrete. If for any two objects Sorry, I was about to say about two different objects, but then it would mean that we distinguish between them. Well, the way out is like this. We define only discrete small categories. Then I have a right to write down that whenever the objects are different, the morphism, set of morphism from one to another is empty. And in a very strong pictorial sense, it is really discrete, there might be some arrows of objects to itself, and well, by the axioms there is at least one arrow to itself, but no arrows connecting the different objects. Now we are going to give an immediate application of this notion. So first of all, let's introduce the new name of category with a nice name, cat. I would say that there are mathematicians who just define this cat as the category of all categories, with the functors as morphisms. I have a feeling that this object is as self-contradictory as the set of all sets, but well, I am not a real expert in this field, and well, some people think that it is illegal objects. However, what is definitely legal is the category as we understand it, following many other sources, the category of small categories. Well, the point is, of course, it is okay with all the arrows if we would consider the category of all categories. The trouble would be when we consider morphisms. All the functors from one category to another one do not constitute a set. Well, there is a wording locally small category that assumes that the morphism constitutes constitute a set, but we'll stick to this understanding. So for our goals, at least for today, it is quite enough to consider the category of small categories, and we apply it in the following way. Just now define, sorry, I have to consult in what order we consider them. Consider the two properties simultaneously. I mean, consider the small and discrete categories. This object, this creature seems very poor as possible, in fact, in the world of categories. However, consider some of them. I have some reasons to denote it like n, though not serious ones. But it allows us to define the families of objects. In fact, when I was a student, I had serious difficulties trying to understand, say, the definition of the product in categories. That will be soon reminded, because I did not understand the formalism in which such a thing existed. And now it is quite enough to consider a family. That is, what does it mean? It means just a functor from the category, from the discrete small category to any categories that we just denote not in quite a standard way. The difficulty is exactly the same as to understand what is a sequence. That a sequence is just a mapping from natural numbers to any set, but with the special notations. Instead of writing x of n as we used, we write x sub n. This is what is this is the family. We should not consider the set of elements of the family, but here is the definition, the concept consistent with our maybe too accurate introduction of the category language. Then more than the small categories, we can consider the small functors with an obvious notations for them, say c to the nth. Whenever it is allowed, we use this exponential. Whenever it is meaningful, we use this exponential notation. Well, let me denote it. So it is the set of functors or families. Well, it is easier to say functors. They constitute the category in an obvious way. So we can use it. And now we can, using this concept and notations, let's introduce one more. The favorite ones from Grothendika. And sorry, I have chosen the letter N. I'm not sure that it is really a good choice, because I wanted to reserve our capital letter I let me write it down, the category of diagrams denoted in the same way C2, I'll try this I. My attempt is not very good. Tech is doing it better. Of course, the diagram is nothing but the directed graph, and in the same way, the partially ordered set, and the category of diagram like this is sometimes a very convenient object. At least the texts of say homological algebra contain lots of objects and arrows connecting them, so all of them are the objects of the unique category. So I'm using N as just a discrete category. Well, I thought about it as N something close to natural number with no set of natural numbers with no obvious morphisms, but the idea is perhaps not so good because well, at least some natural order is imposed on natural number. However, from our childhood we are used to, of course the letter is different, to imagine N like this, and it is precisely the picture we need, a really discrete set of an arbitrary cardinality, however. So this is why I change the fonts. So, well, in a very close future, we are not going to use categories of diagrams. We'll return to them if we have enough time to introduce Untitled homology. Now just use them to define much more standard constructions in the category theory. Any questions about, well, this bunch of notations?
Just a small question.
Yeah.
In the definition of discrete category, not equality means not isomorphic or not equal?
Sorry, say it again.
Okay.
A bit louder, please.
Okay. In the definition of discrete small category, not equality between x and means not isomorphic?
Well, you see, here I had to impose small. As soon as it is small, the objects can be compared, and the equality sign makes sense. Sorry, I have forgotten about it from the beginning, but stopped myself, and this is the reason why the small had to be inserted. Other questions? Okay. So, small and essentially small categories are not yet covered. Let me consult my plan. Maybe I change it, but no. Categories of diagrams. So I hurried to erase the non-standard heading of essentially small categories. And the situation is a bit delicate here because the standard notation is, well, perhaps let me give it just just claiming that we are not going to use this concept. So the category with spine for Russian speakers, categories со скелетом are such categories that there exists a set containing all the classes of isomorphic objects for any object of C. There exists, well, a S in C such that X is isomorphic to S. So I think, I think that the definition is ugly for many reasons. Well, for two reasons. This is not in the spirit of category theory to consider its subsets. Maybe it is not so with small subcategories, but in this definition, it is not at all taken into account. And the other nasty property of such a definition is that it is terribly non-canonical. How there is no way to choose an object to put it into the spine. Well, the true spine of a species, at least a human being, something quite definite, but there are no ways to select a representative of the class of isomorphic object. So I am speaking about it just to claim that there exists an official concept for this the notion we really need. So instead I introduce the concept that seems perfect for me, essentially small category, and I'm proud to say that I have discussed this question with Pierre Deligne, and it is exactly his suggestion. So this word combination belongs to Pierre Deligne. I'm not writing it now, but I've mentioned it in several texts. And it means that there exists, separately from the category, there exists a set M. Just now I confess why I prefer this letter to all the others. In the algebra geometric consideration, these the sets like I'm going to define are going to be the moduli spaces. So exists the set M set and the associate set that can be as well considered as a discrete category together with the association, so C to M denoted by X to the class of isomorphism of X in such a way that that the two objects X, Y from the C are isomorphic if and only if there the corresponding elements of the set M coincide. I would say the basic example is when C is the category of finite sets, then M is the set of natural numbers and the equivalence class is nothing but the cardinality of a finite set. Again, there is a terminological question. I asked in that conversation, I have asked Delin whether they can just call M. Would he like this M to be called the moduli space of an essentially small category? And he said that definitely no. The word moduli is overloaded. Therefore, I suggested after that conversation to call M the catalog of the essentially small category. So a category is essentially small if and only if it has a catalog. Just with this property. Well, a pair of examples, perhaps. So, the category that I have selected before as especially important for us is this 1 over k fields finitely generated. Is essentially small and its catalog, it's, I would say, well, it's catalog or creating its catalog is close to the birational geometry. We are going to discuss it in much more details. However, we could be interested in arbitrary fields. There are lots of nice fields that are not finitely generated over everything. For example, the field of complex numbers. So all the fields like that. We can omit this base field. Of course, not essentially small, because we can consider fields of rational functions in an arbitrary set of variables. And well, it might seem that perhaps I'm not going to write, not essentially small, well, we could bound the cardinality For example, if we are going to do classical algebraic geometry, you can be more or less sure that you are not going to meet the fields with the cardinality more than the continuum ones. However, such a bound is, to my mind, not a good idea. So it leaves away no, say, non-standard and non-standard algebra. Standard, I would say non-standard math. That is extremely interesting. Well, studied intensively both by logicians and algebraists, with all that actual infinitesimals and so on, and some naturally occurring fields also have surprisingly large cardinalities. So I think it is just to say that the mathematics of essentially small cardinalities is quite important and well, quite actual, but we should not restrict our attention to them forever. Any questions about this part of the lecture? Okay, now I think since the next topic is very standard, I think we can almost skip it. And call it the standard constructions. They are all defined in mutually dual pairs. However, mathematically, the dual objects usually are very different. So, in fact, I'm going to consider just two of them. So, products. The first one is products and co-products. So, well, the only problem here is to choose the appropriate notations. Maybe let's start with what we are going to define. So, define the products. Here I forget, I have to choose between different letters. So, we want to consider the family of objects labeled by something, by I. Since here we do not mean that the set of indices has any structure, we use the previously introduced. And so now let's write what we have denoted. So C is as usually arbitrary, X as we have decided. So C, we have two categories here. C quite arbitrary, but of course, as I hope everybody here knows, I don't claim at all that all the products exist in all the categories. It is well, quite useful to run through the categories you know and to think which of them admit products and which don't. So here C is arbitrary, N is, as we have discussed, it is a small discrete category. It rather means that in this definition, we're not going to use any structure on the set of indices. When we are going to use them, it is going to be not a product but a limit, not a product or co-product, but a limit and co-limit. So n like this, and x is a functor from n to c. That we are going to call just the family of objects of an arbitrary category. The most difficult notational thing is to draw what we demand by how do we draw the coordinates. I haven't thought of anything better than, say, xn prime with lots of dots here, meaning, though it's difficult to imagine that, and at this level we have all the components. So n symbolically n prime. Perhaps I use such a wrong notation that could clarify the matter in the 19th century style of notation. And well, the product exists whenever this object can be called product whenever it is supplied for any I, and it is supplied by projection sub I from the product to xi. And as everybody knows, what is demanded, that for any object z, just using the last letter, let's use the standard notation, and here we should imagine as much arrows as the category n contains. So for arbitrary z and say morphisms zeta sub I, and for any n morphism zeta sub I z to x sub n, there exists something I'm not going to denote. There exists and is unique. Well, such an arrow that all the diagram is commutative. Well, you see, in my mind it would take a half of minutes, but it turns out that it is quite a boring business to write down almost all the details. Besides, I should give it the name and write down the commutativity condition, and I believe that everybody knows what it is. So sorry for changing the plan, so there are coproducts as well, coproducts, limits, and co-limits. Perhaps the only thing we will discuss just a bit which of them is going to be limit and which co-limit. So I'm suppressing the well-known notations. Any questions about this besides co-limit? So I erase everything here. At least I believe that I have persuaded you that the notations we have introduced are enough to define all these standard things. I just give the characterization of the category of topological space. I mean one of these concepts is the generalization of union, the other the generalization of intersection, and it is not immediately clear how to memorize the corresponding concepts. My suggestion is that we understand that limits are inside products, while co-limits are inside co-products. Therefore, co-products are close to union, and that means that the relation is like this. So the category of topological space possesses the following, enjoys the following properties. So the arbitrary, it has the arbitrary co-limits. This is the brief translation of the fact. Well, in a topological space, we basically consider the structure of the open sets. So the translation to the main axioms that saying us that the arbitrary unions of open sets are open is like this. It has arbitrary co-limits and finite limits. There are two more axioms saying us that the empty set and the whole space are open, and again they are translated immediately like the existence of the initial and final objects. So if anybody here is inclined to think about general topology, my suggestion is to think or to take some standard book on general topology and see does it need anything besides these purely categorical properties of the topological spaces. In fact, the whole theory of Grothendieck topologies, to which this course is devoted, is nothing but the generalization of the topological concepts. So we just use the standard construction for the beginning. Of course, it is just the first class of the school of Grothendieck topologies. Any questions about that?
Here you mean that arbitrary colimits
Mhm.
so on is in the category that we assign to some topological space X. So for every topological space we have category of open sets.
Yes, that's it, but yes, and these are the properties of the small category of open sets with its only structure, partial order. Well, so sorry, it is not quite clear for me what I should omit and what discussed, but I hope very much that it is enough about standard construction. At least they do not really contain subtle points. So now we are going to discuss a much more delicate question that perhaps cannot be solved, be considered as completely solved. And for so its name, how did I call it? Just equivalences. There are several various equivalences. In categories. And by the way, in the conference to which I have referred recently, where I have discussed the terminological issues with Pierre Deligne had a 1-hour talk about the equality sign in mathematics. So, well, the first thing I'd like to stress is that we have the set of isomorphism instead of equality. This claim should be perhaps understood in two ways. The first one is purely logical. Again, I have no idea about the logical background of the listeners of this course, but those who had some courses, who have taken some courses in mathematical logic, perhaps or were just interested in it, perhaps were interested in the fact, perhaps knew the fact, know the fact even now, that there are theories with equality sign and without equality sign. As for me, I think it is quite a bad idea to teach the beginners to this part of logic because it's quite difficult for a student that was recently in a high school to understand why one should forbid the equality sign. However, this is exactly what the category language is. And constructing the logical foundations of category theory, we should think how we avoid this sign. So this is a formally logical point of view. I would say that there is a more informal one, that is thinking about sets is like this. And there are two basic signs. If this is X, we can ask about anything in the world, whether it is an element of the set X or no. And more than that, given two sets, perhaps we know that there are X and Y. The question whether X equals Y is the most legal and the most important question in the set theoretical mathematics. We should think about the categories somehow. Well, I suggest writing the boundary not so clearly, though of course when the category is defined, we know very well, we understand completely what is an object of the category and what is not. However, there is no such thing as being equal. Instead, there are, for any two objects that are, there are set of arrows in both directions. Perhaps to be 100% sure that this is well understood, we rewrite that X is isomorphic to Y if and only if there exists the morphism I from X to Y and the morphism J in the inverse direction, such that I composed with J, here I have to look at the picture to write it down in the correct order. Don't remember, so I composed with J is applied to J, so equals identity sub Y, then and logically and, here we should not think anymore, are the identities of psi. So it is more complicated, of course, than the equality in the set theory, but throughout we agree that identifying any objects needs a special tool of identifying. As I heard from my teacher Yuri Ivanovich Manin, nothing is equal to nothing, and the identification needs a special consideration. This is exactly, this is what I was trying to explain. So this is the first kind of something like equality, and it is insufficient for many purposes. We'd like to identify not only the objects inside a fixed category, but also, and maybe much more importantly, to establish relations between the categories themselves. And then the next step, I hope no questions about that. The next step is understood better if you consider parallelly the concept of homotopic equivalence. We discussed, at the end of the previous lecture, we have discussed the homotopic mappings, continuous mappings, but with the aid of continuous mappings, a much more fundamental concept, that of homotopical equivalence, is defined. And my advice is to keep it in mind, and if somebody needs a refreshment of it, to read something about it, because the category equivalence is defined exactly in the same way. And first we define the natural transformations of functors. So suppose now we have two categories and two functors in the same direction, f and g here. So this natural transformation is a system for any object in the category C. We have a morphism, and I need a while to see how it is denoted, or maybe I better first write down the diagram. So there are two objects of the category D. We can write it down. G of X are objects in D. Well, and having F of what is the condition? Let me see. F of X x some letter, well, transformation is like this, tau sub x f of x to j of x, it can be understood only as a morphism in the category D, and then for any object y in C and any morphism alpha from x to y, would we have the column in C, the column in C, and then f of x, then f, here we have alpha, sorry, here, yes, we have alpha, and here we have, the general principle is that the diagram is restored in the only way, sorry, oh, we don't need it. So besides that we have f of the square is raised. This one, the square is constituted, f of y, and then there is j of x and j of y, and there should be the appropriate names for all the arrows. So whenever we have alpha, we denote in a standard way alpha lower star. Then we have tau sub x and tau sub y, and the last one is what? Another alpha lower star, of course. Yes, here alpha is defined by f, and here another alpha lower star. So this notation is too economic. We do not include the functor in the lower star. So this is the definition of the natural transformation of functors. Now the next concept in the series is category equivalence. It follows again the homotopic scheme. So the f from C, let's write it in the same way. F in one direction, but here perhaps we use another letter, so well, maybe H here. And well, we have not defined the composition of functors. Oh, sorry, I have skipped, since the time is over, I have skipped the equivalence of functors. I mean the possibility of natural transformation of one to another and back with all the standard diagrams. And then as in homotopic theory, this should be isomorphic to the identical functor of the category C, and the other one to the identity of the category D. Well, here I have to stop in the middle of the explanation. So it is about 1/4 of the planned lecture for today that I was able to cover, and we have not discussed the problem. Maybe I just outline what I was going to discuss. So suppose we are considering the equivalence in the set of vector spaces. We have not introduced it. However, the notation is obvious, and then the V is simply isomorphic to its dual, but is canonically isomorphic to its second dual. I'm going to apply all these constructions to discussing of the difference between this and this character, but between the lecture you can think about that yourself, or maybe tell me now or write if this is quite obvious for you.